this session for those who were not able to make it. So I'm going to start just a review from starting from chapter 2 and try to hit on the main points of the course. And if you have any questions, just stop me and ask questions or clarifications or issues that might relate to questions on the final. So in chapter 2, we were discussing material properties, and one of the things that we discussed is how to make materials stronger, but at the same time do not sacrifice ductility. And the way we do that is by cold working, and that is by loading. If you take the load versus the cross-sectional area, so as the load increases, the cross-sectional area will decrease up to a point when the material starts to flow plastically at the load Pi. And then when you unload, the unloading is elastic. So the unloading elastic, you recover a part of the cross-section from AI to AI prime. So this elastic recovery that you can see here, I'm going to try to get maybe a different pointer. Just 1 second. Yeah. Yeah, the pointer here. Yeah, this pointer. So can you guys see the pointer? Okay, so when we unload, the cross-section recovers a small part from AI to AI prime. So this is an elastic recovery. And then the cross-section has decreased and become smaller than before. So the original is A0, and then it became AI prime. So there's a permanent set. So for all practical purposes, we ignore the elastic recovery from AI to AI prime, and we define the degree of cold work, W, as the change in the cross-sectional area divided by the original, and therefore ignoring the elastic recovery, it is AI A0 minus AI over A0. And therefore, the new area after the unloading is the original times 1 minus the cold work, the degree of cold work. So if we take this to the extreme, if we just pull all the way to failure, so that we have a final cross-sectional area that's very small, this degree of cold work becomes very special, and it's called a reduction in area, and it's an indication of the ductility of the material. So going back to the idea of cold work, once we know the cross-sectional area after plastic deformation, we can compute the true strain in the material. And once we know the true strain, then we utilize a constitutive relationship called the Ramberg-Osgood, and this relationship gives us the corresponding stress. And that's the procedure to find the new value of the yield stress. So basically, if you look at it, the true strain is the natural log of L over L0, which is natural log over A0 over A. And now we know that this ratio here is 1 over 1 minus W. So that can be determined immediately from the degree of cold work. So we set this on the side, and then we start using this into the Ramberg-Osgood relationship that has two constants, M and sigma 0. Sigma 0 is a strength coefficient, and M is the strain hardening exponent that is usually around 0.2 to 0.3. So once we have that, we can, from the degree of cold work, we can obtain the new yield stress. the new yield stress will follow this relationship, the Ramberg-Osgood, knowing the value of the true strain, which is computed from the work hardening coefficient. So that's the story with the yield. The story with the ultimate is that at the ultimate strength of the material, whether it is cold worked or original, we can only sustain a certain level of force, and therefore the force is equal to the stress times the cross-sectional area, and therefore we can obtain the ultimate strength SU prime from the stress strain curve, engineering stress strain curve, S sub U, by knowing the ratio of A0 over A, which is 1 over 1 minus W. So it turns out to be that S ultimate prime is SU over 1 minus W, greater than S ultimate, and we can now compare the yield stress, the new yield stress, to the new ultimate stress, and decide if they're too close, material is brittle. If there's still some gap of greater than maybe 80%, then there's enough ductility in the material. So this is an example here that S yield is 32, S ultimate is 49.5. The failure strength of material is 91.1. This is not used. The coefficient sigma 0 for the Ramberg-Osgood is 90, and the strain hardening exponent is 0.25, and the failure strain is 1.05. That's not used again. And then we have 15% cold work. So immediately we take the cold work, put it into this formula, determine the ratio of A0 over AI to be 1.176. So this is basically can be used to find the true strain by taking the natural log of this to get the true strain. You notice that is 0.1625, very close to 0.176, which is the axis and the one here. And using Ramberg-Osgood, we obtain the new yield, and the ultimate is obtained by force conservation, as I mentioned. So these are very close, so it means that we have hardened too far, and most likely this will be a brittle design. So we had the problems like this before, and we understand now the meaning of cold work and the characteristics of the stress strain curve here, and loading and unloading, and the meaning of all of the symbols on this curve. Now there's a part that is qualitative in chapter 2, and the qualitative part is to familiarize us with some of the basic terminology in the strength of materials. So you've got to read that, and here's a summary. For instance, the hardness, we have two different methods for measurements of the hardness. Rockwell or Brinell. Both methods depend on indentation. So you just indent, and the force divided by a predefined by the area of the indenter is like a stress, but they call it hardness because it's not exactly stress. It is just the force divided by some contact area between the indenter and the material. So this is used to do non-destructive evaluation of properties, because if you have like a pipeline, you don't want to cut it up and start doing testing, stress strain curve, but you want to get an idea if the pipeline has degraded and became brittle or not. So you do a hardness, either Rockwell, ABC, depends on the indenter size, or Brinell, which is a spherical indenter, force over the area. And then engineers use a correlation between the hardness number and the strength. So for example, for steels, it's 0.5 HB. HB is the Rockwell in KSI. So it'd be very nice if you can just indent and get a number, like you have actually a dial, you just get a dial, get a hardness number, and then you multiply it by 0.5, you get the strength of the material. that would be great instead of doing extensive testing. So another property is impact property, in which we have Charpy test. The Charpy test is a very heavy hammer, and this it rotates around a pivot, and then the hammer is dropped at distance h, so it gains energy mgh by the time it hits a sample, and this sample is under conditions that you have a notch, and the notch is a location for a crack to propagate. And then we keep changing the height h until the sample breaks. So you get a curve at which every time the sample breaks, then we have an energy that's absorbed to make it break. And that's the impact value that we have. We plot the impact value in foot-pound versus the temperature. And generally, we get a curve that looks like a step like this. So it has very low values at low temperatures and high values at high temperatures. And in between, you have a transition. And this transition is known as the ductile to brittle transition temperature. So hopefully, all of our components will have a very low value of DBTT, meaning that they have enough fracture toughness or enough impact energy characteristics at normal operating temperatures. Obviously, if we are working in a very cold climate, like in the Arctic, then we must have a DBTT that's extremely low so that we don't have brittle behavior. Also, we need to be cognizant of strain rate effects and temperature effects on properties. So there are a number of, I don't know why it's not showing here, but we have results in the book that shows the ultimate strength as a function of strain rate. Generally, the strength, either ultimate or yield, they increase as a function of the strain rate. Material becomes stronger. And as a function of temperature, they decrease. So you can just have an idea about these qualitative properties. Another property is creep, and the creep is the strain. The property is the strain versus time. So initially you have an elastic prompt response if you put a load, constant load, and then beyond that, the material starts to deform as a function of time. And it has three regimes. One is a primary, which is very sharp increase in the strain, and then a secondary regime in which the slope of the line is constant. So the slope is called the steady state creep rate. So this is constant creep rate. And then you have a tertiary regime in which the material starts to accelerate in deformation because you have a lot of voids inside the material and the interlink, and it falls apart. So these are all qualitative properties of the materials. Any questions? I can't hear. Somebody has like echo, so I'm not really sure I can hear. Everybody's hear me? I just need some response. Am I okay, or should I increase the volume? Or
I can sort of hear you, Professor.
Oh, okay. All right, good. Thanks. Because I just needed some feedback because I'm not sure if people are hearing me. Okay. So the other properties are material numbering systems, and those are the different societies of automotive engineering, Institute of Steel, American Institute of Steel, and ASTM, UNS, Unified Numbering System. An example is that the alloys, they are given letters like G for carbon steel, A aluminum, C copper, and S steels. And and then if you take the case of steel, usually you have 5 numbers. The first 2 give you the composition of alloy steel. Alloy steel meaning that you put magnesium, chromium, nickel, and so on for different characteristics. And then the second 2 digits are for carbon content. And then the third is a special. So they have composition, things like 10 is for plain carbon, 13 manganese, and then you go into nickel in the 20s and 30s and chrome. And then as you go up higher, then you get more expensive materials, alloying elements like molybdenum and chromium. So for example, G52986, it means that this is carbon steel, this is a carbon steel, carbon or alloy steel, and 52 means it's chrome. It's kind of expensive material, and 98 is the 0.98% carbon, and it has some kind of treatment, alloy heat treatment that's indicated by 6. Also, you might want to familiarize yourself with the manufacturing methods, casting, for example. They have sand casting, shell casting, investment, and powder casting, and methods of hot working, and how you control the grain size and so on. So this is more qualitative information. So if there's something on the final, it will be in the spirit of descriptive information, either properties or manufacturing techniques to give us the appropriate material properties. Okay. Now we move on to stress. So the next item. So now this is kind of a quick review of material properties. Now we move on to stress. So the stress is everything related in the course is related to power transmission. So we know that the power is equal to the torque times the angular speed. If everything is in MKS system, this is watts, this is Newton meter, and this is radian per second. But we usually have either in watts and RPM. So you have a formula H is equal to Tn over 9.55. It's the same thing here, but we just converted radian per second to RPM. Or another more useful formula for the US standard system. If the power is in horsepower, and the torque is usually in pound-foot-inch, and the speed is in RPM. So in this case, you divide by 63,025. Now the stresses, we reviewed some of the main stress systems, and we wanted to be familiar with the equations, how to apply the equations, and in what type of application. First, we started with thin tubes. And the thin tube is a very simple system. When you have a pressure inside, you do force balance, you get a tangential stress that is equal to pressure times the diameter di over 2t. And if you make a correction for the maximum, this is an average value. As you know from pressure vessels, the tangential stress has a distribution function, so it goes from high to low, from the inside to the outside. But in the thin tube approximation, we take an average value, and then we could also use an enhancement for this by adding the thickness T to the diameter, the inside diameter, and that gives us the maximum value of the tangential stress. So the longitudinal stress, if it is close to, then the pressure is going to push on the top, and the force balance gives us that the axial stress is half of the tangential stress. So you have PD over 14. So there's a problem here that we have an aluminum tube has outer diameter 8 inches, T is equal 1/4. So the ratio of T over D is 1/32, which means that it's a very good candidate for using the thin tube approximation. And if the maximum stress is 12 KSI, we want to know what is P, and then we want to compare that to using the thick cylinder equations. So the solution is that we get the inner diameter by subtracting twice the thickness, and then the inner radius, and then the outer radius. So the inner is 3.75, outer is 4, and then the T over I, to ascertain to ourselves that it is less than 10%, that is okay to use the thin tube approximation. And with that, we can use this formula to, since we are allowed 12.5 or 12 KSI, then this is allowed, we know everything except the pressure, and the pressure is 774 PSI. And then the exercise is to compare that to a thick pressure vessel. And the thick pressure vessel, the equations, if you look at them, they are a function of the square of the radius, all of the radii square. So you have an inner radius and an outer radius and a generic radius. So you always have 3 radii, one inner fixed, one outer fixed, and one generic where you evaluate the action, like the stress. So in this case, the maximum is going to be at the inner radius, and then we use the thick pressure vessel formula with the generic radius being equal to Ri, and that gives us 12,000, which is the same as the thin tube, so it shows us that the thin tube approximation is correct. One other thing that you need to also know that either in the thin tube approximation, the radial stress is assumed to be 0, very, very small, 0. In the thick pressure vessel, the radial stress is always equal to its maximum at the inner radius, and it's equal to the applied pressure negative, because it's a negative stress, because compressive. So it is minus 774 at the inner surface. So that's kind of, you have a bunch of formulas for the pressure vessels, and then specialized for thin tubes that we can practice on. Then we have other axially symmetric systems. So the pressure vessel is axially symmetric. The rotating rings or rotating flywheels is also an axially symmetric system, but it has a body force. And the body force is the density times omega squared, depends on the angular speed. And we have a formula. As you notice here in this course, there's lots of formulas. We don't really spend a lot of time in derivations, but we need to apply them. So if there's something on the final, then you're gonna make your own summaries to be familiar with these equations. And usually I provide also the required formulas, but you have to be familiar with them so that you can select them quickly, so you don't get confused between the different symbols. So in these formulas here, you have tangential stress and the radial stress of the same exact nature. The only difference is that the tangential has a plus and the radial has a minus here. And then the last term that is proportional to the radius squared, the generic radius squared. Generic radius is this R that doesn't have any subscript. In the tangential case has 1 plus 3 nu over 3 nu here, and the radial doesn't have. And then questions like this. So if you have a rotating flywheel and you know the maximum failure strength of the flywheel, then determine the angular, the maximum RPM? So this is a very typical question, which means that you want to solve for omega. That's kind of the bottom line. So how does it work exactly? You have a strength, let's say you're given a yield strength and a factor of safety and the failure criterion. So the failure criterion could be, for example, the distortion energy. So distortion energy, which we will summarize, will have a von Mises stress that you can find from sigma T, sigma R, or you can find another criterion like maximum shear that has the difference between sigma T and sigma R over 2. Because we have like 3 principal stresses, and if it is a thin disk, then the third stress is 0 or approximately 0, and therefore we can use, we can find the maximum shear, which is the difference between this 2 over 2. The problem is that we don't know what this quantity is the maximum because there's a generic radius here. So if you look at the problems in the book, there is a location for maximum value of sigma R by taking the derivative of this equation and finding the peak. And it turned out to be that the location is at the square root of the product of the inner and outer radius. So this is pretty well established. While the tangential is always high on the inner and it comes down to the outer. So that comes with practice because you just plot these equations fine. So you conclude that, okay, well, if there's a failure, it's going to be most likely on the inner surface. And then you substitute for the generic R at the inner surface, and then you try to satisfy the failure criteria at the generic surface. So this rotating. One other point is that I wanted to point your attention that if you're using the US customary system, the density is not going to be in kilogram per meter cube. So you have to convert it to pound force, because this has to come to be something in force. So the density has to be, you have to equate the mass times the acceleration of gravity is equal to the force. So you get a conversion that has the gravity of in a British system or US customary system, which is 32 foot per second square. So the foot also you have to convert it to inch. So it becomes like 386 inch per second square. So you get a factor that is important here to determine this maximum RPM correctly. Moving on to more axisymmetric systems, you can see that they are interlinked. We started with the pressure vessel, and then the rotating rings, and then now the press and shrink fits. So the press and shrink fits, the trick in there is that if we have an interference, as we discussed in class, we have a hole and a shaft, and there's a delta in between them that we would compute from the tolerance. You compute from two items. One is the tolerance, which is how well you finish the surface, and the other one is called the deviation, which is a symbol. Like if it is interference, it will be something like N or P or S or U. So with these two numbers, we can determine the delta. And the delta, once you know the delta, then that creates an interfacial pressure between the inner shaft, which is assumed to be hollow in this case, but it could be solid also, and the outer shaft. So the geometry is that you have a hollow inner shaft that has R inner. There's a interface at capital R, and there's an outer shaft at R sub 0. And they could have different elastic properties, E inner and E outer, nu inner, nu outer. And then there's a pressure at this interface here. that is generated from the interference. That pressure, we have this formula for it, just a very long formula that we derived in 156A, and it gives us an interesting idea that the pressure is proportional to delta. In other words, it's not proportional to delta square or delta cube. You give me the geometry and the properties, and I'm going to crank out this number, and that number will give me so many KSI per inch. So if delta is an inch, then every inch gives you, let's say, 1,000 KSI. So if the interference is 0.001 inch, then the pressure will be 1 KSI. So that number is some labor here that comes in finding that. But once you have the pressure, then the problem is you forget about the press and shrink fit, and you deal with the subject to pressure vessels all over again. So you have two pressure vessels, one outer that has an internal pressure, and one inner that has an external pressure. So the inner has an external pressure, P, and the inner is 0, and the outer has an outer pressure 0 and internal P, and then we have formulas that we used to determine the tangential stress and the radial stress in this whole system, and then we could apply failure criteria again to decide if the interference is way too much or too little. So that's kind of the design question, is it too much, too little? Do you have enough pressure? Do you reach yield when you force fit? And so on. Another question that can come here is that this pressure here is useful in transferring torque. And the idea is that the pressure is normal to the surface, so there is a tangential force that is proportional to the normal force via friction coefficient. So the ratio between the normal and tangential force is the friction coefficient. So the pressure we converted to a tangential force, tangential holding force, when we multiply by the friction coefficient, and that tangential force is the one that's going to transfer the torque, because they have the force here times the distance from the center gives us a torque. So all of these are kind of connected ideas that may arise when we analyze the shrink fit or the press fit problem. Are there any questions here? Okay. The next type of problems will be a thermal stress problem. And the thermal stress problem is that if we are constraining, the material is going to develop thermal stress. If we're not constraining it, it's not going to care, right? So you might ask, why is that? Well, if you just have a pot and you're heating it, it is constrained because the sides are not expanding the same as the bottom, so it's going to warp, and you're going to have some thermal stress. But if you have a bar and you put it homogeneously into a big oven to heat it slowly, then it will expand at no thermal stress. So if we have a rod and we have a complete constraint, the stress is compressive minus epsilon times E, and that is minus alpha delta T times E. And if it is a constrained plate, then you have this factor 1 minus nu, but it is also compressive stress. So this is a very simple problem, but we can also look at maybe two bars connected with one another. So if you have one bar that is expanding at the same temperature, the other bar has a different alpha. So you have alpha 1 and alpha 2. They're not going to expand the same, but they have to be compatible. So one is going to be under compression and one is going to be under tension, and they might curve. So these are the, I think I discussed that in class, the problem that Timoshenko solved, and it's used in thermal actuators or clocks and things like that, and also to give you a temperature sensor, because from the radius of curvature, it tells us what the temperature is. So we need to be familiar with it and understand that the thermal stress is dependent on the temperature expansion coefficient. And that it boils down to materials that are phase center cubic or HCP. They have very high thermal expansion coefficient, not so good, aluminum and magnesium. Steel is also not so good, 17. These are in units of parts per million, means that you take that number, multiply by 10 to the minus 6, and that's the strain that you get per degree. So the cast iron is lower, the lowest is tungsten, and I mentioned there's a metal called Invar that has almost zero thermal expansion coefficient, and a lot of people look for materials that have very low thermal expansion coefficients. The next subject that we dealt with is curved beams, and in the curved beam, we have a coordinate system that again has an inner radius, Ri, and outer radius, Ro, and it has a neutral surface that is described by Rn, and that is not exactly in the center of the geometry, so it's offset. So if you take that system and put it sideways, take a cut and put it sideways, then we have the neutral surface is lower than the centroidal surface. Centroidal is midway between top and bottom, and the neutral is a little bit lower, and the difference is called the eccentricity. And in these types of problems, the geometry has to be worked out first. So we have to find the neutral radius. R sub n is usually not known from the beginning. It depends on the cross section and the inner and outer radii. So we have to find that one. And once we find it, we can find the eccentricity E. Once we find the eccentricity E, then we're kind of set, because we have two surfaces, one at the bottom, one on the top. The bottom is going to be under tension if the moment is applied as shown in the figure. The bottom is going to be under tension, the top is going to be under compression, and we can find the stresses, and these are stresses in the tangential direction. So these are tangential stresses. So you have, first job is the geometry. So we have neutral axis is A divided by integral of dA over R. Luckily, if we're lucky, the cross section is rectangular. Then the area is B times H, and the integration is pretty simple. You get H over ln of RO over Ri. If the cross section is not rectangular, don't worry, there's a formula, because we're not really here to evaluate integrals, but there's a formula that we can use for a particular cross section. But for all practical purposes, if there's a problem, then we usually use rectangular cross section for demonstrations. And the stresses now are, remember, in a beam is my over I or mc over I for maximum. C is top or bottom. So that's what the word C, but the letter C. But for curved beams, we have a CI and a CO. They are not equal. So because of the shift in the neutral axis. So instead of MC over I, we have MCI over the area times eccentricity times Ri, which has the same units as the second moment of area. It's inch to the power 4. And we have the same now for sigma outer. We minus MCO over AERO. So problems like that would include maybe hooks for cranes, C-clamps under forces. So the problem could be two parts. One part is first to get the moment at the worst location. So you have a C-clamp and you have a force. Then you have to kind of find where is the maximum moment, would be at the kind of the edge of the clamp. Or if it is a hook, then the hook has a force, and then you find the maximum moment. Once you find the maximum moment, then you apply these formulas to find the stresses. And usually we have an additional force. So what we have here is a stress due to a pure moment. But in the applications we have, there's always going to be an axial force in addition. So if I have a hook, there's going to be the force that has to be transmitted in addition. So that force can give you tension that is very simple, the force divided by the cross-sectional area. So you don't forget about this contribution as well. Okay, finally, the last part of the stresses is contact stresses, and those we need them for roller bearings and ball bearings. So we have contact forces. We have two contacting surfaces. If they are spheres, then you have a contact area. And this contact area is like a circle. So you're pushing a sphere against a sphere, then the contact area is a circle that has a radius. This is a Hertzian solution. It's elasticity solution. Gives you a circle. And the circle is the cubic root of this formula here, where F is the force. E1 and E2 and D1 and D2 are the diameters of the balls that are contacting and the elastic moduli. So we know now the circle radius. Then the problem is that you get a pressure. So it's always, you can see now, the whole ideas of contact, like in the case of press fit, we were looking for a pressure, the interface. Here we get a radius, then we have a pressure on that radius, which is 3F over 2 pi A squared. And then we have a formula for the stress distribution. This is a result of solution of elasticity that gives us a stress distribution and the maximum stresses. And similarly for cylinders, we have something like that. But if you think about it, this is just for information. The problems, contact problems, they are kind of standard, and there's not much one can determine from there at this point without a lot of labor, because you have a lot of like substitutions in here, and therefore we wouldn't have to worry about it for the final. Next, so now we summarize materials, we summarize stresses. Now we're going to summarize deflections, because that's the second, like the part of the design, material selection, satisfy stresses, some kind of failure criteria, satisfy deflections and rotations. So the deflections, we define the stiffness constant K as F over delta. And our goal is to go over every element and find that stiffness. So if you have a bar, then we use the strain as delta over L, which is the sigma over E, and that gives us an expression for the force over the extension, which is the stiffness. So the stiffness is A times E over L. If we have a round torsion bar, then that torsion bar has a angle of rotation, theta, given the torque. So it's TL over GJ. And the torsional stiffness is the relationship between the force divided by the displacement. So in this case, the force is the torque, and the displacement is the rotation angle. So T over theta gives us GJ over L. So if you have a bar and you torque it and you let go, then it's going to be like a pendulum, and it has frequency determined by this torsional stiffness, KT. If we have a beam, the basic fundamental equation is the radius of curvature is rho, so 1 over rho is the curvature itself. The curvature is proportional to the moments, and therefore the curvature is m over EI. That's 1 over EI is the proportionality constant. And to a first approximation, the curvature is equal to the second derivative of the deflection, y double prime. And the slope is equal to the first derivative of the deflection. So theta is the slope, and the theta is dy by dx, the slope, small angle approximation. So the problem that we have in the deflection is that given loading, solve statics problem, find the reactions, and then find the deflection. So this is kind of the general way that we set up the problem. And which means that if I have the loading, I have to find the shear force diagram, and I have to find the bending moment diagram, and then I divide that by EI. That gives me the curvature. And then I have to integrate this once to get the slope, and I integrate this once again to get the deflection. So it's a process by which the y 4 primes is equal to q over EI. Q is the force on the beam that could be concentrated or distributed. Y triple prime is one integration, you get V. Another integration, you get m over EI. And then we can integrate this again one more time and another time to get the deflection. So one way that we learned that's very useful is singularity functions. Why? Because we have concentrated loads. And in the past, people broke the beam into pieces, and they said from x equals 0 to 5, do this, from 5 to 10, do this, and so on. That's the way I learned. I didn't learn singularity functions. And then when singularity functions were defined, it was easy because you can write one equation, but you just have to interpret it the right way, which is, again, section by section, how things are actually happening. So the singularity function starts with a doublet, and the doublet is like one force up and one force down. It's concentrated moment, and it is represented as x minus a to the minus 2. And the meaning is that it's 0 everywhere except at the location x equals a, and it goes to plus or minus infinity. And it has the property that if you integrate it over the entire domain, it becomes x minus a to the minus 1. And the meaning of x to the minus a to the minus 1 is that it's an impulse function. And the impulse function is like a concentrated load at x equals to a. Again, the meaning is that it's 0 everywhere except exactly at that point that it goes to infinity. But it has a property. In other words, when it goes to infinity, it doesn't mean anything. It just is something goes to infinity, but it has to, you have to describe it more. You can say, if I integrate it over the entire domain, then it will have like a bend. So the integration of this x minus a to the minus 1 over the entire domain gives us a step function, which has a value from this is 0 up to x equals a, and then beyond that point, it is equal to unity. So that's a step function. And then the step function, which is x minus a to the 0, if I integrate it one more time, then that gives us x minus a to the power 1. And that's a linear ramp with the meaning that it is 0 up to x equals a, and beyond that, it is proportional to x. So we've done several examples of this type, and I'm not going to go over these examples, but just take any questions on the singularity functions at this point, or on any other aspect that I covered already. Are there any questions? So singularity functions. Okay, other things that we can do with deflections is that we can solve problems that are indeterminate, like they call them indeterminate beam problems. So I think there are several examples that are a little bit more difficult than the standard. Like this is standard. I just do integrations. It's nothing, no big deal once you understand the meaning of the singularity functions and how you kind of move from one to another. So it would be pretty straightforward. What is not straightforward is that if I'm constraining, like if I have a beam and the beam is constrained at some additional point, like this beam, for example, it has two reactions, R1 and R2, and one force in the middle. So it's totally determinate, and I can write Q for this, and I integrate it once and twice and so on. I can get the entire story about the deflection. But if I'm just putting a little constraint at where this pointer is here, then all bets are off, because the constraint is going to give a reaction, and the reaction cannot be solved from the equations of equilibrium. And therefore, the deflection method becomes useful because it can convert the problem to finding that reaction by knowing the deflection at a point. So it's like, you know the deflection at this point to be zero, or it could be even not zero, like I can have let's say, a constraint that is a little bit below, like not exactly at the beam, but just slightly below. And I can, if I know this gap, then the beam is going to deflect up to this point and then stop there. So whatever it is, I have a constraint that is either zero or finite, and I have a deflection equation that I can obtain by integration, like by this method, but then I would have an additional reaction in this equation that is unknown. So I solve for the deflection, and I find the unknown reaction at that point. So you gotta go back and review. There's a couple of problems on links. If you have a link coming down and then it's connected to something else, and then there's some constraint in the middle, so you have these connections. Usually, we solve them with some kind of deflection method. So the singularity is one method, but another method that is more direct and faster, if we're interested in redundancies, is the Castigliano, because the Castigliano gives us the deflection directly at a point. So it is very useful in redundancy problems. It's very useful in point-wise deflections rather than the entire field. And it goes as follows, that the deflection is the rate of change of the stored elastic energy with respect to the force, and the rotation is the rate of change of the elastic energy with respect to the moment. So if we have bending, then the deflection is the rate of change with respect to the force at a specific point in the same direction of the force. I'm kind of repeating that. So it is in the same direction of the force. And then we take the derivative of the elastic energy. Now, the elastic energy, we have several formulas for it. So if it is per unit volume, it's sigma squared over 2e. If it is bending, it's m squared over 2ei, and so on. So you just have a formula for the energy. So the formula for the energy is m squared over 2ei. So if we take the derivative, we use partial fractions, it turns out to be that the deflection is the product of 1 over ei times m times dm by dfi. So there's two functions. One is m, and one is its derivative. So we have to evaluate this one, and then find the deflection due to that. Similarly, for torsion, the rotation, 1 over gj, t times dt by dmi. And for axial, 1 over ae, f df by dfi. So they have the same kind of structure, two things, f and f, so on. So if you look at an example, I have like a beam that is stepped like that, and it has a force F coming down, and I'm interested in a deflection at point A and point B downward. So at point A, it's exactly under the force. So I need to find, do I have bending? Do I have torsion? Do I have axial? And then the answer is that we have bending only. So great. So we don't need anything else. We need to find the energy stored in the bending and then differentiate it. So it's already differentiated for us, which means that we want to find M and dM by dFi. So in this problem is very simple. The F is down. X, you take it from a convenient coordinate center. And in this case, I'm going to put the coordinate center at A. And that gives me the moment is equal to minus F times X. So I have the moment. Immediately, I take the derivative with respect to F, not with respect to X, but with respect to F. And that gives me minus X. So I have the two functions. One is the moment, and the other one is its derivative with respect to the force. Notice that I have I1 here and I2 here, and therefore I have to break the integration into two pieces, and because the energy stored in here adds to the energy stored in here, and then I find the deflection at the end in here. So remember that I told you a formula is delta is equal to FL cubed over 3EI. So that's the formula if the cross section was the same everywhere, right? But here, because two different cross sections, it came out to be a little bit different. But you can tell that it's of the same nature, FL cubed over EI1, but then you have a different factor here. For point B that doesn't have a force, then we assume that there's a kind of a ghost force, Q, redundant force, and then we find the moment in terms of the force Q and take its derivative and then do the integration. So in this case, the force has two components, minus Fx, and then Q is located at x minus L over 2, so it has to have a step function. And then when we take the derivative with respect to Q, the first term is 0. Second term becomes x minus L over 2 times the step function, which means that this is not activated beyond this point. So beyond B, it's activated here. And therefore, the first part is 0 because there's no activation of this function. And then the second part gives me the deflection. Finally, I think I'm going to give this example and stop, is when we have curved beams, then in these problems, when we try to find the deflection, it can be a little bit tricky. So you have to practice a little bit more on these problems. So problems of rings, for example, you have a ring and you push on it, or the ring is maybe like half a circle, and it has some support, and you push on the top. Or in this case, you have a clamp, and then you're pushing in the middle here, and it's bending. So all these types of problems pose challenges. The reason is that if we use a thick cross-section, then the shear becomes significant, the energy stored in shear, and there could be also axial forces that we have to take into account. So it makes more additional terms. So if you look in the book, there's more energy stored in these components. But for practical purposes, we deal with problems that have small cross sections in relationship to the radius, so they look like wire mainly. And in these types of problems, we can safely ignore the energy in shear and axial, and the energy stored in bending is the majority, could be like maybe 90%. And this is the type of problem here that we have. And then, so this is the first challenge. Second challenge is it has integrations that are not straightforward. Like these integrations here, they are just linear. So you just put a straight line and then you integrate. For this, you have to be careful. So if we take this example, we have a force P at point C, and we want to find the deflection at point D, at point D. So we have to put a ghost force here, Q, that has zero value, but anyway, it's there. And then we find some kind of complicated shape. So we have to divide it into one straight section, AB, and then another quarter circle from B to C, and another quarter circle from C to D. Now we notice right away that from C to D, there is effectively no force, even though there is a Q, but the Q is zero. So that part is kind of limp. It doesn't have, it's not tense. So it doesn't have elastic energy stored in it. So we can pretty much ignore that part. We don't have to worry about that part. So the elastic energy will be stored in this section and in this section. So the problem now simplified. You have to find the moment and its derivative in this section, AB, which is straight. So you can put your coordinate system anywhere, like let's say at X, which is at the end, at B here, to make your life easier. And then this quarter circle in which you discard the coordinates with the angle theta. So for that straight section, the moment in any cross-section X at this point here is P times the radius plus X, because you have X coming. See, this is another point, is that the choice of X coordinates is important. So if you choose it from that point, so it'd be easier because X will be increasing this way. So you have P R plus X plus Q times 2R plus X. Take the derivative with respect to Q, integrate, you get an answer. What does it mean? This means that this is not the full deflection. This is the contribution to the deflection as a result of the energy stored in the element AB. And then we have another contribution here, and that we have a coordinate system that is given by, described by theta and the radius and R. So we have theta here. And then we have a system. Now we have, this is P as the applied force. And then we have to find the reactance. And the reactance at any cross section, you have to have three components: a shear, a normal, and a moment. And luckily, we just not gonna worry about V, the shear. We're not gonna worry about the axial to make our life simple. And then the shear, the moment is the one that we can compute as a function of Q and P, differentiated and integrated. Now, the integration is going to be around the arc length. So instead of dx, it will be r d theta. So the integral becomes from linear to theta integral, from 0 to pi over 2. These kinds of problems a lot of times pops out sine squared and cosine squared, or sine cosine, something like that, because you have a moment and you have its derivative. So you get sine from here, cosine from there. So you got these kinds of weird functions, and therefore we just either have to be careful. Usually in the exam we don't have time to apply the square sine formula or cosine formula, so we just kind of give you the result for specific integrations of these functions that you can use in the solution. The last thing that I'm going to do today is buckling, and then I'm going to stop here. Can continue tomorrow, next Wednesday. The buckling is two parts. One is for very long beam columns. So these are, if they are very long, then they buckle according to Euler simple formula. If they get a little bit shorter, then life is not so easy because they can actually yield. So we have to kind of find this condition. So when we say it's a column, it means it's kind of a thick object. If it is a beam column, it means that it can carry some bending and some axial force. If we say a strut, it means that it's like a slender member that is inclined, usually inclined, like in the car. So we have boundary conditions, and the boundary conditions are shown here. These are the four different configurations, either pin-pinned or maybe a roller with a slope that is 0 on the rollers and a slope here, or free and fixed, or pinned and fixed. So these gives you modes. When you solve the buckling problem, you get a mode shape for the sine, like a sine curve that has a wavelength, and the wavelength adjusts itself by these boundary conditions. So the end result is that there's a critical load that is equal to pi over L squared. This is the eigenvalue times EI times C. C comes from these end fixity conditions. So that is the famous Euler formula. And then if we define, we don't like, in this case, I, which is the second moment of area. So we define it as A times K squared. K is the radius of gyration because it has a length scale. And that gives us the critical stress as proportional to the elastic modulus times pi over a dimensionless length, which is L over K. So that's called the slenderness ratio. So if L over K is very large, then we have Euler buckling. And if it is small, then we have yielding. So to the transition between Euler and some kind of approach to yielding is when we take that stress to be half of the yield point. When we equate S yield over 2 to the critical stress, we can find a critical value, L over K1. That critical value is given here, 2 pi squared CE over SY. And that has the material properties in it. And therefore, we can determine if our slenderness ratio is above that value, then it's Euler. If it is below that value, then we use a parabola going from point T to point to 0 here. The L over K is 0. And at this point, we have a yield. We have the full yield. And that parabola is called the Johnson parabola. And it has two constants, A and B, that can be determined from the coordinates of point T and point S. So that's the application of these types of problems is that usually we don't really know the cross-section. That's what we design it for. So we have some kind of length and a load. So we kind of guess the cross-section, find the slenderness ratio, and then if it is in Euler, then apply Euler formula with the end fixity effects, and then find the critical stress, and then we check to see if that is true still in the Euler regime. Fine. If it's not, then we have to redesign it based on the Johnson parabola that takes into account yielding. So I think our hour is up, and we are now kind of up to speed all the way to chapter 4. And maybe next week I can review 5 and 6 and 7. And then maybe on another Saturday, make a review for chapter 13 and 14, where we have the gears and the gear ratios and the gear trains and so forth. This is the area that we're going to be working on tomorrow. Okay? All right, so any questions? Anybody has any questions? Okay, I think we're gonna stop the meeting now, and we'll see everybody tomorrow.
Professor,
Yes,
I have a small question.
yes.
For using the Castigliano's theorem, for curving, if R over H is very large, then we can neglect the shear and axial the contributions of axial and shear, right?
Yeah.
And like for normal beam, normally we can neglect the contributions of the shear force, right?
Yeah.
So
yeah.
so we only consider like the bending and the axial, and we just neglect the shear forces.
Right. Yeah. That's what I was saying. Is like you have the formulas in the book for every variety, because the book is going to be with you when you work or you do research or something like that. But for practical purposes, most of the energy is going to be in bending, and most of the results that we have so far, and therefore we neglect the shear contribution and also the axial contribution, and just calculate the energy stored in the bending. So it is our kind of desire to do that for the purposes of the course, and for having, and also it is kind of consistent with the reality. One reality that if you have a large radius of curvature compared to the cross section, then everything is in bending. Most of the energy is in bending.
Okay, got it. Thank you.
Any other questions? Okay, thank you very much, and then we'll see you then tomorrow.